Hi, I'm Naz. I'm the CEO and founder of Rebel and the author of Developer Life and maintainer of the Rebel 2e crates. I believe that open source comes from an open heart and from the joy of coding. In today's video, we're going to cover a very interesting topic. It's actually a very important topic to me, and it's all about performance, specifically software performance and accounting for almost the physicality of the hardware in which the software is operating. So just to give you a bit of background, I actually went to school in the 90s at Virginia Tech, and I studied to be a computer engineer. So my major was computer engineering, and I had a minor in computer science. So I did both hardware and software. So I studied all kinds of really cool stuff like chip design, and I actually went to master's, but dropped out of it to start a company. But my master's was in computer science. I was doing a bunch of research stuff on parallel computing back in the day. Java had just happened. But to kind of give some context, so back in the day, I did a bunch of stuff with 8086, 8088, 386, and the 486 were like a big deal. But a lot of things have changed. But in many ways, a lot of things have remained the same. So one of the things that's been magical about the computer industry, the semiconductor industry anyways, every 2 years roughly since, I don't know, late 70s, Moore's Law, Gordon Moore, who worked for Intel, his laws says something like every 2 years the amount of transistors in a given physical area of an integrated circuit doubles, and that's largely been the case up until about 2015 to 2020 when that ended. And so today, for example, if you look at a desktop CPU, they tend to have multiple cores rather than one really fast core. And like I have a CPU with I think it's I forget, some 8 performance cores and some 12 efficiency cores. So the speed of a CPU, I remember back in the day when 1 gigahertz was a big number. Today 6 gigahertz is a big number, but that number hasn't changed that much if you consider in the maybe even 5 years ago, 10 years ago, 5 to 6. 5 is probably more on the higher end, and 6 is on the even higher end. But then you have to, cooling becomes an issue, and at some point, just the sheer amount of thickness of wires that are painted through using ultraviolet on silicon starts to become a factor, like how thin those wires are that are etched using lithography, which is pretty amazing. So given that the compute, let's say per square inch of an integrated circuit, the number of transistors is no longer doubling, what implications does that have to software, the speed at which software runs on hardware? And this video is going to be a little bit talk heavy at the start. I actually wrote an article about this on Developer Life, which I'll cover in detail in the first half of the video, and then we'll get into the live coding section after that, where I'll use Rust examples to illustrate a lot of these concepts. So yeah, with that, let's get started. Okay, let's get into the article first in order to get a sense of what memory locality, actually what memory latency is comprised of. So and where does this even come into play? So as I had mentioned earlier at the start of this sort of the intro talk, that Moore's Law is finished, and essentially what that means is that the implications of that in terms of performance is that can't really count on single-threaded or single-core performance anymore as a way to sort of lift or provide an uplift in performance by doing nothing. So essentially the same code that's been written already won't necessarily get any faster as it used to in, let's say, before 2015 or something, or before 2020 even. So for example, the next 5 to 10 years, assuming single core count or single core performance stays about the same, essentially for single-threaded workloads, code isn't necessarily going to get faster just from CPU improvements. But it's not a lost cause, because that's what this video is all about, is what can we do about it. And one thing to note though is that so this means CPU-bound code, which means code that has a limit on how fast it goes or what it does. That workload is tied to CPU, won't necessarily get an uplift simply by upgrading to the latest CPU in the future. So I would actually say single-threaded CPU bound code, Because if you can parallelize it, it's a different story. The more cores, the more cores, more better in that case. But this is for single-threaded workloads. Another one is that when people consider big O notation to do algorithmic analysis, emphasis on opcount, or number of operations that a CPU can execute per clock cycle. So, for example, 5 gigahertz clock means that a lot of like 5 giga, like 1 hertz is 1 operation a cycle, so 5 gig operations per second the CPU can perform. So when you look at the op count or the operation count, that's how big O analysis does its like analysis to find like the upward bounds or whatever for certain algorithms. What it does largely do is completely ignore. It does not account for memory latency, which means that today we're getting into the world where, and this is what we're going to jump into right away, is that in order to access data from memory to read or write, whether it's the stack or the heap, it consumes quite a bit of time. And computers have gotten fast now where CPUs are really quick, and the amount of time it takes to get data in and out of those CPUs is not quick. It's quite slow, actually, especially as we get farther and farther and away from the CPU die. So, yeah, big O analysis needs an update. So another one is that modern CPUs, we kind of touched upon this with the first point, is that we have more CPUs now, but not necessarily faster CPUs. So parallelism is the answer for that one. It's a quick one. So I really recommend going through these links. They're really, really good. Like this is a good video, another great video on why, like, what types of data structures are conducive to better memory efficiency. There's this concept of memory locality. So for example, if you look at a vec of structs, and let's say this vec contains a bunch of, let's say, pointers. So there's a vec, and each vec, the vec has each item in that vec is a pointer, and that pointer is another struct. So let's say that we allocate a bunch of strings on the heap. So we have like 1, 2, 3 that's on the heap, and then we take references to each one of these strings and we put them in the vec. So the way a vec itself is constructed, the way the string itself is, and we're going to see an example with this. The way string itself is constructed is that it contains it's a vec of U8. So the U8 is actually allocated in an array, which has a pointer saying where does the array start. It has a length and a capacity. The length is how many items are in there, and the capacity is a total amount of pre-allocated space that this array is how big it is in memory. Whether there's heap or stack, it doesn't matter. So in that scenario, like a string is a vec of U8. So one string, actually, the backing store for that is an array. So when we have let's say a vec of pointer to string, then in order to be able to traverse through those strings, you kind of think of it this way: like the vec itself has an array whose type is pointer to string, and they have a certain size, so those are sized, and that array, the backing store of the vec, contains an array, and each item in that array is a pointer. In order to access each string, we have to load in memory. We have to go find where that vec starts, then for offset into its backing store, its internal array, and then dereference and jump to another location in memory where we have to go get another array. So all these jumps, these pointer jumps, they're quite expensive, and we'll look at like how expensive. So, but that was just a kind of a convoluted made up example of where you have like a vec of pointers, and let's say the vec of pointers is the string slices. That's the pointer to strings which are allocated on the heap. So in order to improve or reduce the number of jumps, if these data structures can be flattened and co-located, roughly speaking, this is not always possible, but if data structures are designed with latency, this memory latency from the ground up, then we might actually get a lot of gains in performance just by doing this. So this is kind of like, if you watch this video, it kind of goes into this where instead of thinking about object-oriented design or functional programming, this is taking the approach of data-oriented design. Pretty sure this video is, yeah, it's for C, but it's still relevant. So yeah, that's a really, really good video, actually, this one. Then I have another one. Oh yeah, this is just, this memory latency thing has nothing to do with Rust. It's just how CPUs and RAM work in current CPU architecture. And so whether you're using Java, in this case, whether you're using C or C++, all of this is not going to go away. And then, so before getting into the deep dive of latency, here's a couple of best practices that you can sort of, this is the sort of what can you do about it? One is flatten data structures for better memory locality. So there's these ways of doing, you can use like things called your own custom memory allocators. You can use arena allocators if you find yourself allocating and deallocating a lot of small structs over a period of time. That's one approach, which is essentially flattening, essentially considering that, okay, I'm going to use an array as a backing store, because once that array has been allocated, I've taken the hit for allocating it. And then if I can sort of use that array and somehow with a couple of other data structures, like, and we're going to use the example of RingBuffer. That's why I picked that specifically in the live coding section to see how we can do this in practice, where we're going to be very clever about how we allocate and deallocate, because technically we've already pre-allocated, but we're going to figure out a way to mark when a slot is in use in that array, and then craft algorithms around that to make sure that we're not having to excessively allocate or deallocate memory, because memory allocation is also expensive. Anything related to memory, just leaving the CPU and then headed towards memory, just that little jump costs quite a bit. So obviously this is not avoidable. There's many use cases for using vec and string. In those cases, these structs also typically have a with capacity method, and that's a good one. If you know how big your vec or string will be, if you allocate it with capacity ahead of time, and a lot of APIs in Rust will give you a sizing hint for what the capacity should be, use them, because that ends up yielding a lot of performance. Because then you're not necessarily, so the way, like, for example, a string works is if you allocate a string of size, let's say with capacity 5, so the backing store, this is not accurate exactly, but let's say the backing store will be pre-allocated with 5 chars, 5 U8s. As long as my string is within the bounds of, like, I can add or remove chars, it's fine. As long as I don't exceed the capacity of 5, I don't need to reallocate the backing store, and I can just reuse it. Because strings under the hood are implemented with, I think, a null, like, basically if you have a vec of, if you have an array of, let's say 5 chars, U8s, and you say A, B, C, and then null, then, or, \0, then essentially ABC, that's how it's null delimited. That's how the string knows how far it can go. So as long as you don't exceed the capacity that you have allocated with, then you can add and remove items. So when you remove it, the array will basically shift one, and we'll see this in an example as well. So essentially, we as long as we're not exceeding the capacity, performance is good for the most part. So with capacity is a fantastic method to know and use wherever possible with sizing hints. It's not possible always to know what the size is up front. So when possible, use it. And then this is one other sort of helpful tip, is that there are these crates called smallvec and smallstr, and they're part of the server crate, and which is backed by the Linux Foundation. So they're not going away. These are essentially inline replacements for vec and string. So instead of allocating on the heap, this allocates on the stack. And there's certain behaviors that this gives you that might be beneficial in certain use cases. And I'll cover this in the examples in the live coding video later. But yeah, these are these are interesting alternatives when you're thinking about memory. So it's inescapable, this fact that it's going to cost to allocate. So we can allocate up front and then amortize the cost over the use of that. Let's say it's struct. But if we're incurring the cost of allocating or reallocating for every operation, that might be too expensive. But depends. Again, having said all of this so far, without actually testing, there is no intuition really that will give an answer. That means that what feels right, what seems like it should work or shouldn't work, isn't necessarily the right answer without testing. So profiling and testing is very, very important part of this journey. Like get your code working. Think about locality up front when you're designing the data structures, but once you've designed them, you might be surprised that where intuition doesn't necessarily yield the results that you might have expected. So with that, let's do a deep dive on memory latency. And I think if we look at the table of contents, then that's I'm going to talk about cache lines and what is memory latency, and then we'll talk about like how the stack and the heap play into this. Stack and the heap doesn't matter; they're still memory, so latency is still there, heap or stack. There's certain differences in using one versus the other, though. We'll talk a little bit about memory alignment. Rust compiler pretty much takes care of this, but I'm going to show examples of what this is, how you can actually see it. Global allocators. This is another good one. I had touched briefly upon make your own memory allocators. So you could do like global allocators or local allocators. I'll show you an example of this. Jemalloc is a good one, depending on, again, what your use cases are. If your program is primarily single-threaded, then the default memory allocator is good. If it's multi-threaded and it does a lot of small allocations and deallocations, then jemalloc is good. And then we'll look at examples for smallvec and smallstr, and then finally go over lots of code examples that you can study after this video. So with that, let us get started with memory latency and cache lines. At the most fundamental level, when we talk about CPU instructions and memory, like, why does this matter? Well, in order for your program, so when you write some Rust code and it creates a variable and you assign a value to it, like a number, and then you take the value of that variable, add it by 1, and then use print line, like in a very basic program like that. Like, what do we care about memory? Well, in order for a computer, a CPU, in order for it to execute instructions, it needs to have some data to operate on. So for example, for x86 architecture, there's instructions that essentially take some data, load it from main memory, put it in a register, perform an operation on that register, then take the value that's the new value that's in the register from, let's say, add by 1, and then save it back to main memory, something along those lines. And so that's where these registers and L1 caches and things like. So register is essentially the closest thing. It's like on the CPU itself. It's like you can think of it as like tiny amounts of memory that you can use to store sized variables, like local variables. Then just beyond that, we have L1 cache, and so like each core has its own L1, L2 cache, register, and so on. So parallelism, you can almost think of this like, even though we're describing one CPU, it's actually one core, but RAM is shared between multiple cores. So there's multiple layers of caches, so that the CPU, what happens is, in order to load, let's say, some data from memory, it has to go out to main memory based on the address where, let's say, this particular piece of information is stored. It has to go look up that address in order to get the value at that address, and then bring it in. So so in order to perform let's say an operation on a register, let's say the register's already been loaded with data, to do an add operation is pretty quick. It can be done in like 1 cycle. 1 cycle is like, remember the 6 gigahertz, 5 gigahertz, this is like 6 giga cycles per second. So each one of these cycles is what we're talking about when we say cycle. So register operations are super fast. It's per clock cycle. L1, L2 caches, L1 is about 10 to 50 times slower. L2 cache is about 50 to 200 times slower. So now we're like, essentially the CPU is idling when it's waiting for, let's say, data to be loaded from L1 or L2 cache. So L1 registers are not that many, relatively speaking. L1 is a little larger amount than that. L2 is a larger amount than L1. You can even have L3 caches and so on. So the idea is that the processor makes sure to keep these things as full as possible. But caching is hard. Cache hits and misses and cache eviction policies and writing things that have been changed to cache. These are notoriously complicated, especially when we're dealing with instructions like nowadays with the modern x86 architectures, or even any other modern architecture. So even what the CPU will try to do with microcode is it'll try to parallelize as many of these instructions as possible. So it'll decompose one instruction in assembly, let's say, into much smaller instructions, feed them into pipelines that it's trying to predict. There's all kinds of optimizations that go on to make computers faster because Moore's law doesn't hold anymore. So just to kind of give for some perspective, as soon as that CPU touches RAM, we're now 1,000 times slower. Let's say 500 to 1,000 cycles that a CPU is idling, waiting for something to show up from RAM. And for this reason, CPUs don't, let's say you have 1 byte that you're reading from RAM. What the CPU will do is that instead of just reading 1 byte, it'll load in the case of x86. Where's cache lines? It will load roughly 64 bytes of data. So even though you ask main memory, say, hey, go get me 1 byte from main memory, it'll actually load that 1 byte plus 63 bytes after it. And I'll put that, and so the minimum amount of data you can access from main memory is the width of your cache line. And for Apple M processors, it's 120, let's see, I think it's 128 bytes, and bytes, not bits. And for Intel stuff, it's 64 bytes. So my computer right now is 64 byte cache line. So that's a minimum amount of information that can be loaded, data that can be loaded from main memory. So every time one of these cache lines gets filled, we're talking about, let's say, 500 to 1,000 times slowdown. So you can imagine algorithms that go out to main memory a lot, they're jumping all over the place. You can imagine if there's cache misses outside of these 64 bytes, it can be quite expensive. So that's what I mean by locality. When possible, if data that's going to be accessed, let's say not once but many times, can be put beside each other, there's a good chance it'll be picked up in these cache lines, so that the next let's say variable after the one you're looking for, let's say there's a loop, it loops through many items in an array. If all those items were beside each other, it makes the execution much faster, because we're taking into account, okay, is the cache line, how big is it? Is the memory that it's being fetched from RAM, is it going to fit in the cache line? Yes or no? How many cache lines is it going to take to fill this? So, but just to kind of, what I'm trying to show with this table is that it's not really accurate to count operations, like with big O notation, for example. It's not just the number of operations, the opcount. It's more than that. It's every time you're going out to RAM, that's 1,000 ops. And depending on how you write your data structures, and then the algorithms that operate on those data structures, that can make a pretty big difference here. And again, I want to emphasize this: once code has been written, don't use your intuition. It's important to actually instrument it and figure out, what it's actually doing at runtime. There's all kinds of really cool ways to measure. There's all kinds of different tools that you can use. But yeah, it's important to, for example, flame graphs is one way, but there's all kinds of other ways you can instrument this. So instrumentation, collecting data about what's actually happening is key, instead of using intuition. To kind of extend this a little bit further, let's say that you're accessing memory in the GPU. That's about 1,000 to 2,000 times slower. An SSD is roughly 10,000 to 100,000 times slower. So that's like fast SSD using PCI Express 4 or 5 or whatever. So that's to give some perspective, like, whoa, how much slower is that than a register? So, and there's technologies, I'm sure, Intel is working on stuff and a whole bunch of other companies where maybe one day the SSD latency will come down to RAM. And maybe like with modern CPU architectures, they take the RAM and they put it like, in order to increase memory bandwidth and memory speed, they put it like on the die, like in the system on a chip, like right beside the CPU, as close as possible. This is why there's a lot of, let's say, laptops, or even, laptops have like soldered RAM because it consumes less power, and it's also relatively fast compared to like the SODIMMs that you usually find. Those are, the farther the SODIMM slots are, from the CPU, the more wires there are, and that can lead to slowdowns as well. So that's why there's ranges here. So SSDs, even if we reduce the latency for it to be close to RAM, we're still talking about 500 to 1,000 times slower than register access, right? So something to keep in mind. And also, remember, the cache line is only 64 bytes. That's a really, really, really small number, if you think about it, 64 bytes. So when we go out to the network, so let's say these are operations that require network access, you're doing some kind of TCP connection or HTTPS or whatever. We're talking about a slowdown of 1 million to 10 million. This is why async makes a lot of sense when you're waiting for something to resolve. That's going to go out over the WAN, right? So that's why it's like, you tell Linux, hey, let me know when some data is available in the socket, and then when that data is available, Linux will use epoll to tell Tokyo, oh, okay, hey Waker, go check if this is ready or not. This, that makes sense. So while a network operation is underway, like your CPU locally is just twiddling his thumbs. LAN traffic is faster, but still almost 1 million times slower than register. And if your internet hops take you cross-continent, because then now you have to go through these wires underwater to get from one continent to another, that adds more time. So hopefully this table gives some perspective into like why latency matters. And I think latency is the name of the game when it comes to improving performance, given that Moore's law is no more. So yeah, and this is just, please take a read through this. It explains kind of like what I kind of went through at a high level. But yeah, and it's interesting, like these second, millisecond, microsecond, nanosecond, we're going to get into some of these numbers soon. So yeah, cache lines, I kind of went over this as well. Take a read through this, kind of covered all of it. And there's all kinds of interesting algorithms that are used to figure out how to deal with cache misses and hits and how to properly do this kind of caching. It's not easy. Okay, so that kind of ends the section on like latency when it comes to relative to register. So actually I had this really nice picture I need to add. I think I put it here. This one. I need to add this. I did this picture actually. I'm gonna add this to that article so that we have this visual. So it's kind of like gives you a sense of like, okay, what are the latencies here? So there you go. So with that, now we can. With that said, now that we've covered cache lines, now we can talk about stack and heap. And right after this is we're going to jump into code and start exploring a lot of these concepts in Rust. Okay, so in your Rust program, when we allocate memory, so local variables are allocated on the stack, you can allocate arrays on the stack. But something like a vec or a string, caps S string, is allocated on the heap. So the basic difference is that heap memory is growable to, whatever. This is boundless, so to speak. Logically anyway. Clearly there's physical bounds. But then operating systems also have virtual memory, so they'll use, like if you allocate a ton of memory and it's not fitting in RAM, physical RAM, it'll basically overflow into virtual memory. there's this whole thing in Linux operating system called pages and page faults, which kind of take care of loading, segmenting or chunking memory into pages and then loading them in and out of various sources, and then detecting when a page is dirty and then writing it back to, disk, for example, or wherever. But all those details aside, like from a sort of simplistic programming perspective, we have stack and heap. Heap is where if we don't know the size of something, or if the size is really big, if we're going to allocate and deallocate a lot of stuff, we probably want to put that in the heap. The stack, on the other hand, is typically for Linux 8 megabytes by default for your whole process. So if you allocate if you have like one variable, which is like a 7 or 8 megabyte array, then you'll more than likely have a stack overflow. So when we use the stack, we have to use it judiciously. See, there's actually ways to change the stack size on Linux per process. So you can actually even find out what your current stack size is. You can do ulimit-s. So let's see if we do, where is this? So let's say on my computer, if we do ulimit-s, it's this is reported in kilobytes, so that's 8,192 kilobytes, about 8 megs. And so I can do like -s, and I could change that number, and that's just temporarily. But if I want to do it permanently, I can go and I can futz with this etc securitylimits.conf. So what is this? Soft stack. Oh, I see these. I don't have anything here, but yeah. So you can play with this in the Linux kernel. If, for example, certain workloads require you to have much larger stacks or much smaller stacks, this is something that you can mess with. But this is generally the sort of the default 8 megabytes. And for kernel threads, which we're not talking about, it's different. So here, let's talk about the sort of the when you would use one versus the other, and how does it impact latency and locality. Latency applies whether it's on the stack or the heap. You can allocate a fixed size array on the heap just like you can on the stack. On the stack, generally speaking, because the way the stack is arranged, all local variables, because they're sized, are literally on top of each other, so locality is good. However, if you want to resize it, that's hard. So for example, deallocating on the stack is easy. When your function returns, the stack pointer gets changed, and so there's actually no need to deallocate anything. So it's just gone. It's pretty quick to deallocate. Memcopy is the same, because memcopy is not about allocating or deallocating. If you actually need to, let's say copy, like, so you have a stack, let's say, I'm sorry, in the stack, let's say you have an array, or in the heap, you have an array of like 5 items, and you fill it with 1, 2, 3, 4, 5, and then you remove one of them in the middle. It's going to shift all the items one to the beginning of the array, and that's going to be a memcopy, and that's going to be expensive whether it's on the stack or the heap. It's immaterial. So yeah, those are the kind of things you have to think about between heap memory and stack memory. Like, if you don't need, depends on your use case, but I just wanted to mention, yeah. So often faster if you have predictable access patterns. Cache utilization might be better for stack access, quite simply because all the memory is physically on top of each other. But then obviously there's downsides, because it's 8 megabytes, and that 8 megabytes is for your entire process, not just your function. So be careful of doing stack overflow. And when the stack overflow happens, your process will just exit, which is not good. So yeah, we talked about the super. Okay, cool. Now allocation and drop, kind of already talked about. It's like, for stack, it's pretty much free. Memcopy costs the same regardless. And when we're doing allocation on the heap, we're going to be using basically libc and malloc to do the allocation, and free. I mean, we aren't, like, standard type Rust standard library is, and so this is kind of like what some of those numbers are for allocation and deallocation. So as you can see, that microseconds is bigger than nanoseconds. As you can see, like the heap, let's say for 500 kilobytes in a made-up example, it might give you lower performance. But then if you need to add or remove, again, it depends on the use case. Like it's hard to say based on these numbers, like, okay, this is the right answer, that's right. It completely depends on your workload and your data structures and your algorithms and what you need this code to do. But this is good to have some ideas of, like, what some of these costs are. So one thing with heaps is that when you go to there's such a thing called memory fragmentation. So that's something that might end up, let's say, taking some time if the operating system has to go search for enough pages to be able to fill your memory request. And so this is where these global allocators come in. There's this, the Rust standard library comes with an allocator, which is optimized for single-threaded workloads where you're not really making or destroying too many small structs. But if you have a multi-threaded workload where you're constantly creating and deleting small structs, then jemalloc is better tuned for that use case. And I'll show you when we go to the live coding part of this video how we can set that up. So yeah, so there you go. I mean, please take a read through this. There's some interesting stuff in there if you haven't seen this before. And with that, actually, now we start the live coding part of the video, and the rest of it I'm just going to demonstrate with code. And please refer to this developer life article, as a reference. And also, in terms of like feedback, if you like this style of video, please give it a thumbs up and subscribe to the channel so you'll be notified of future videos that I create. But one thing I want to show is that if you wanted to provide feedback on a particular video, every single video that I do ends up having an issue that's associated with it, which is actually in the description of the video. So if you have some feedback, thoughts, and comments, just go ahead and add that to this, to basically here in GitHub issues. I used to have a Discord, but I shut it down. I really didn't know how to use it. So, and sometimes I'll do polls, posts on YouTube with polls. I don't know. We'll see if that works out or not. So yeah, with that, yeah, so that's one way to give feedback. You can also email me. Where is this? Or you can also reach out to me via email, or you can reach out to me via LinkedIn if you have questions about any of this stuff. So yeah, just wanted to talk about that because yeah, you might be wondering, because I turned off comments on the videos. All right, so now with that, we can start the hands-on live coding part of the video where I'll demonstrate all these concepts. Okay, let's start up VS Code and see if we can get started with this hands-on coding video. So I want to make a yeah, memory locality, that's right. And I want to tell Code Insiders to actually reuse this VS Code instance, so I don't have to spawn a new one. So let's see. Okay, cool, perfect. So one thing I want to do actually, I'm going to add a feature flag actually. This will make sense in a minute. This feature flag is so we can actually deconstruct and see what the constituent elements of a vec actually are, and explain why we need this yeah, this thing called into raw parts. But okay, with that, let's start our first. So first thing we're going to do, first example is just examining string and vec and string slice, and what they look like, from a memory allocation layout, or actually let's just say memory allocation perspective. I think the allocation and layout, and then we're gonna do more stuff with alignment and global allocators and stuff like that. So let's see, let's do string and vec, because these are very common heap allocated data structures. So, and then we'll also look at stack allocated versions of them, of course. So Another thing actually I want to do in order to make this work is I have to make sure I'm using the nightly tool chain. So for that, I need to make a this one actually, and here I can say tool chain, and this will be channel nightly. Okay, cool. This puts it in the nightly tool chain, which allows this particular feature flag to actually take effect. So with all that set up, let us also do this CFG test, and we're going to call it StringInVec test. So what are we testing in StringInVec? This is our to do. So one thing we want to do is look at how what exactly are the constituent elements of a string, and then go from there, and then look at like what a string slice looks like under the hood, again from a memory perspective. So the first thing, actually just add some imports real quick. I'm going to do cargo add rebel 2e because I want to have some colorful output. So let's do this test, and so the first thing we want to do is memory layout of a string. So let's look at what a string looks like from a memory perspective. So let's see. Oh, actually, this is just I want to do some pretty printing. Let's see. What is this? Lizard green. So I'm going to say something like string memory layout. Okay. So we just run this. It won't do much. It'll just print. Basically, once it finishes compiling. Wow, that is. Oh, didn't even. Oh, that would help. Okay, didn't actually print anything. Okay, there we go. String memory layout. Oops. Okay, so now what we're going to do is we're going to create a string, and not hello world. We're just going to do 0, 1, 2, 3. Yep, to 9. And this is easy because like 0 has the ASCII value of 48 in decimal, and I think like 30 in hex. So make it easier for us to see, like when we examine the byte values, what's inside of a string. So this is what I meant when I was talking about like deconstructing a string into its constituent elements. So this is the sort of the safe way. So so here we can do something like we can say something like safe way to deconstruct string, right? And you'll see what I'm talking about in just a moment. So here, so if you notice the autocomplete, this actually is exactly what this does, but we're not gonna use that right now. What we're gonna do instead is we're gonna say let the pointer is something like s as pointer. So that essentially, given the string that we've allocated, we can now get its pointer address. Then we can say, we can get its length and we can get its capacity. And this we can say println, we can say pointer. So pointer, I think we can print this as a pointer. So there you go. And then we can put length and capacity. There we go. Okay, so let's run this and And let's see what this looks like. Check that out. So it goes pointer, that's an address value in memory. The length is 10 and the capacity is also 10. The length and the capacity are the same is because when I say string from, it got the length of this, and that's how it set the capacity, and it just so happens that it then filled it with you know, this string literal. So basically is this, so it's like that. So it basically, you know, the static, this is basically baked into the text part of the binary, I forget the name of the Linux file format. What is this? Linux, what is Linux? I think it's ELF binary file format called, is it ELF? I think it's ELF. Yes, so in the ELF file that's generated, this is actually in the text. There's a section of the ELF file which has the literals which are basically baked into the binary. This is that. That's why it's a static lifetime for this reference, because it's referencing it from the binary itself. Okay, so this is a safe way to deconstruct a string. We have the pointer, the length, and the capacity, which is awesome. So now let's look at like a slightly different way, which is let's see. I think VS Code looks like it has frozen up. What is going on? Let's restart it. Not sure why it's being so flaky. Okay. So where were we? Okay, so the safe way, we got that. Let's see if this runs. Yes, it runs, and there's our pointer, length, and capacity. Wonderful. So now let's look at the a different way to get at the same thing, and that will be using that into raw parts code that we saw. This is, it's still safe, but using this one, this feature flag or whatever. So this thing, so here we will say, so foreground, yeah, no, this is still safe. This is another safe way. And another. And so we call this thing called into raw parts, and it gives us same thing, pointer, length, and capacity. And when we print it, we should get the same results. Look at that, same result, no surprise there. So now let's look at this thing called transmute, which is essentially it's a function in the standard library that allows you to take a pointer to whatever it is, interpret those bytes as whatever type you want, and then hope for the best. So this is the unsafe way, using transmute. Okay. So let's see if this is even correct. Unsafe way to deconstruct a string. So we got string. Why is it making a string again? So let's do this. I think it's going to be. Actually, my VS Code hung up again. Let me do this. Maybe I should switch to the stable version of VS Code. Something strange is happening. Let's see, is this working? Oh, right, that won't compile. Okay, so so this is the transmute thing that I was talking about. So here, what we're gonna do, so under the hood, a string is actually a vec of few weights. So now that we've sort of seen it as a pointer, a length, and the capacity, using transmute, we can also see it as a vec of few weight. So, so for example, So this over here, we're deconstructing it into a pointer length and capacity, and here we're going to be deconstructing into a vec of u8. So actually, this is not correct. We're actually going to do something like unsafe standard memory transmutes. This is a from, and this is a to. So we're not going to do this. This actually doesn't work. You can do usize, usize, usize. It doesn't. It actually doesn't work, and there's reasons why that doesn't work. So we can't just later on we'll be using transmute to transmute a string slice into this tuple, and that will actually work. But that tuple only has 2 items in it. But this, if we did this, it's going to produce garbage. So what we can do instead here is we can say vec of u8, because that's how Rust represents strings. Caps S strings is a vec of u8s. And here we are going to get like that, vec of u8, and then we can say print line, and it's just that we're, I don't know why this is not just working. And here, if we run this, let's see what is going on here. Oh, so S into raw parts actually consumed it. So let us do this. Let's just make a new string. So for this one, we're just going to go ahead and make a new string. So we're going to say less, whatever, S, I called it S, so we'll call it, let's just call it another string. Okay, so we have another string. We're constructing with the same string literal. It doesn't really matter one way or another. But here, what we're going to do is, okay, now that we have vec of u8s, let's see what we get out of this. And look at that. We get 48, 49, 50, 51, blah, blah, blah. So to give some perspective, here's our S key. Let us see. Oops, where did it go? So we see this, right? So let's ask our handy dandy, can you convert these ASCII values, ASCII codes into your character codes? So this will be something like, so as you can see, what we got from here, which is 48, 49, and all the way to 59, is actually representing these chars, 0, 1, 2. And we could also, you know, instead of asking AI, we could also use the Rust standard library to do this, but why not, right? Here we go. So this is to kind of show that, you know, under the covers, a string is really made up of 3 things: a pointer to the heap, which is, you know, the starting point for memory allocation, and there's an array that's allocated off size capacity, but it's not filled. So the length is how many of those items in the array, how many of those slots actually contain values. So that's what this is. And yeah, so there we go. That is the first of many examples. And I have to see why my VS Code keeps freezing up. What is wrong with this? Okay, so then we can do our next example after that. Okay, hopefully I have my VS Code issues sorted. So I think it was OBS. I had some settings that weren't really working properly. Okay, so now let us see. So the next thing we can do is, now that we know how the memory layout of a string works, let's look at how the memory layout of a string slice works. So let's see, fn mem layout string slice. So here, the string slice is, let's run this. It should just print nothing. I mean, just whatever. That's great. So the first thing we want to do is create a string slice, and here we can say s equals hello world, and then here we're going to deconstruct this using transmute. using the technique that I said it wasn't gonna work. I mean, we can do it the safe way, like, sure, why not? We can do this. So we get like, oops, safe way to deconstruction. Like we get a pointer and a length, which is, this is correct. That is actually 13 characters. This is very similar to what we saw with the string, and let's try to do unsafe way using transmute. So here we have what is this doing? No, this is not correct. Why is it turning into a string? Anyway, let's just move on. So, so here we're going to do the raw parts are going to be unsafe, and nope, it's not going to be a vec of u8. Nope, nope, nope. This is going to be a const, there it is, a const u8, which is just a pointer, and then this can also be mute if it's a mutable pointer, but whatever. For us, it's just, it's a view into that memory. We're not modifying it, so that's why we have const and not mute for here. And then so essentially this says, okay, take this string slice and interpret the bytes that this is pointing to as this followed by this, a tuple of this followed by that, a pointer followed by some u size. So in my case, 64-bit value, u64. So now what we can do is, actually, why don't we just do this, deconstruct this here. So we can say pointer and actually, no, it's not capacity, because capacity is only for allocating structures. This is just length, because we can't change the capacity. This is like, it is what it is basically, because it's a view into what's in memory. This one we had a capacity, which is, you know, because it's a backing store for the array, for the string, which is an array. Okay, so here we can get a similar kind of thing where, oh, okay, here's the pointer, there's a length, but the way we got it is using unsafe code. So let's run this, and it should, let's see what happens. Look at that, it's the same. Okay, so both the unsafe and the safe way produce the same result. So let's see, let us now do one more example related to this. So this is the final part of this first example of string and string slices, where we're going to make a string, get a slice into it, and then examine like where they are in memory. So here, this is basically mem layout string. Let's just call it string slice 2, because it's both. It's actually string and slice, something like that. Okay, so let's just, okay, so we're going to say let's see, string and string slice, whatever that is, memory layout, and then here we're going to make a owned string. We're just going to say hello world, but then we're going to get a slice into this owned string, and it's going to be the first 5 characters. So we can say assert equals slice is hello. So that's basically what we're doing. I hope that makes sense. So the owned, this is owned, that means it's allocating in the heap, and this is a view or a slice into this already allocated struct. So we're not allocating anything. This is just essentially pointer into whatever's been allocated here, but it's a slice, and starting at the beginning, but only going 5 characters, so it's only going up to hello. So now we're gonna get the now that that's done, we can get the let's say we're gonna get the slice pointer. So let's just deconstruct the slice. Like we're gonna basically compare the, we're gonna deconstruct both owned and slice and see if if let's say they're pointing to the same chunk of memory, which they should. So here we got the slice pointer and slice length. let's do the owned pointer, and let's do the owned length. So obviously the owned length is going to be different because that's 13. So so here we can say something like cert length is it's going to be 5, and this one is 13 because, you know, that's, yeah, there we go, perfect. So far so good. So now we can let's say light, yeah, what is this, light yellow, green. We can say comparing slice and sure. So whatever, it's all of the above. So here we can say, okay, if the slice pointer is the same as the owned pointer, which is, you know, what we expect, and we should also make an assertion. Let's see if this runs. Well, check it out. Slice and owned point. Slice and owned point to the same memory location, which is correct. That's exactly what we had anticipated. So we, you know, this is basically it would be something like green. Actually, let's make it blue. Is there a blue? Yes. And we can say print line. By the way, this is the Rebel TUI just that I'm using to colorize this output. You can call this FG, whatever, pink or something. Yeah. So as in like, this is, you know, it's not right. Obviously, this is not going to get triggered because we know already that the assertion is that they're the same. There you go. Slice and owned point to the same memory location. So we know that this pointer thing, the slice pointer, is the same. Whatever this value is, it's the same. Okay, excellent. Which is, you know, that shouldn't come as a surprise. And then what we can do is that we can say, okay, what are the let's say, actually, there's one more thing. For owned, we also have the capacity. So here, let's just dump for owned, so we can say FG light yellow green. This is owned, you know, info. And here we can say something like, and then we can say slice info, and just to kind of see. So owned info has one more piece of information than slice info, which is, you know, we have pointer, length. So let's just do this. Actually, so the pointer is in both places. The length is in both places. The capacity is only with this guy, with owned. Because of, you know, one is a slice and the other one is, so as you can see, look at that, capacity is 13. So that actually totally tracks. It is what we expect. And so that with that, that's the end of this example, and then we can move on to the next one. So next let's take a look at memory alignment and what all that means. So before we get into it, let us start in a file. This is going to be example 2, alignment, and let's see. Okay, cool. So and then let's go over alignment real quick before we get into it. So what alignment so let's say that you have a struct in memory, and that struct is actually let's take a byte. Say you have a byte, a U8 that you're going to put in memory, and it contains, like, this is a bit of made up example. It has 8 bits, and then let's say that it has a value of, actually no, I have a better example. Okay, let's say that you have a Boolean, and a Boolean is going to store either 0 or 1. So 0 or 1, like, you can't access a bit of memory. That's too small. So in order to be able to address a chunk of memory, that address has to be something that can be addressable. And so, for example, in this case, the bit would be, let's say, turned into a byte, which is 8 bits, and then when it's all zeros, it would be, let's say, so essentially the first bit of that byte of that 8 bits, the first bit would be used, and the rest would be padded. So essentially, this notion of alignment, it's when you have a type which takes up a certain size, in order to be able to address it, you have to have certain multiples of some number that you can address it by, and for values that are small, you essentially pad the width up to that alignment. So so for example, in you can actually develop a pretty quick intuition for it. So like I have a 14th gen Intel CPU. It has, let's say for U size, it uses 8 bytes, and so the size and the alignment are the same. So like for example, if I were to store a U size, it's going to consume 8 bytes. Even if I put the number 1 in it, it's going to pad the remainder of the bits with zeros. So it's going to be 0, 0, 0, whatever, a lot of zeros, just to store the value of 1 in a U size. So that's essentially padding and alignment. So it's pretty straightforward. The Rust compiler takes care of all of this. I just wanted to show some semi-interesting sort of examples. And again, this is not really practically applicable, but let's try this. So let's say we want a test where we're going to create a struct. And we can say this is test 1. And this is going to be something like a struct demo, and demo is going to have in it A. I don't know why B is 32, but okay. So this contains, the size is 1 byte, and the alignment is also 1 byte. Kind of makes sense, right? This one is 4 bytes, aligned to 4 bytes. This one is 2 bytes. And so if a number is, doesn't fit in the 2 bytes, pad it until you have 2 bytes filled in, and that's the alignment. So now let's see what the size is. So we can say size equals this, align is that. So as per our intuition, we can say, let's see, the size is going to be 1, let's see, 4, 5, 6, actually, is it 8? Maybe 4 bytes, 2 bytes, 8, 4, 2, unless this one, let's see, the size is it 7? You know what, let me just print this first. So let's do this. This is FG lizard green. We can say this is size of demo, and then we can just do, let's see what values we get. So we say yellow, green. So we're gonna have like format, byte size, and let's do, so this is gonna be like, let's say, size and alignment. Let's see what we get. Interesting. Size is 8 and alignment is also 8. Oh. 8. Huh. That makes, let's see. What is the, I don't think this is correct, because that's right, there's no way the alignment is 8. Okay, so the size is 8 and alignment is 4. Okay, I get the alignment is 4, because like if you think about it, like it's good, the alignment is going to be the, let's see, because when we add all these up, essentially the alignment is going to be the one that's the largest. It's going to be for the U32. So that makes sense, but I thought the size would be, wait, U32 is 4 bytes, so 8 times, actually, let's do this. What is the size of the struct? So 1, 4, 2, 12 bytes. But it is actually 8. That's probably what it is on C or something, but on in Rust, what is the size of the struct? I was expecting 7. Let's see. Okay, so a U8 is 1 byte, then 3 bytes. Oh, of course, because so even though for U8 the, oh my goodness, okay. So it's going to be, for the whole struct, it's going to be 4 byte boundaries. This is 4 bytes, makes sense. And so, okay. So even though this is 1 byte, it's going to end up getting padded to 4 bytes because the alignment of the struct is 4. So this is going to take a 4, that's going to take a 4, that's going to take a 4. Wait a minute, now it's, but because this is Rust, this is 2. Oh my goodness. Okay, 3 bytes to align to a 4 byte boundary. B is 4 bytes and C is 2 bytes. After C, the struct size is multiple of largest alignments. Holy moly. So, okay, so Rust alignment is pretty epic. Unlike C, it's as you can see, it's not simple, and it rearranged the ordering of these things so that it would compact into a very small form. So if we run this again, let's see what we get. So the size is 8 bytes, and so let's see, how did we get 8 bytes? So the field of A, let's see. So, wow, this is unusually complicated. So the field of A is size 1, offset is 0, it pads it with 3, okay, bytes. Then B is 4 bytes, so that's 8. Wait, what? Rust will reorder and pad. Okay, the minimum size to fit all the fields, the correct alignment is 8 bytes. So if we do it naively, we come up with 12. But if we do it like Rust would do it, then it ends up with 8. Okay, that's pretty awesome. So there you go. Rust compiler is pretty epic, and it does super complicated stuff under the hood. So I'm actually glad I showed this example. So yeah, I was expecting it to be 7, but it's actually 8. So let's look at the another variant of this, which is what if we were not using Rust rules, so to speak, and we did this thing. It's there's this attribute we can say represents C. So now it won't use the Rust layout. It will, or alignment. It will use C alignment, and the C alignment is going to be, this is going to be 12. So basic, because it's like the more simplistic. Well, actually, I forgot the assertions. So this I would assert to be 12 now that I know, or now that we know. And then so here we can say assert equals, nope, this is going to be 12, and that's going to be 4. Okay, I say that quite confidently. Let's see if this works. Oh yeah, cool. All right, so this one actually, so yeah, this is before, I should say, this is naively without reordering. This is, how do you say this? So basically, if you reorder this and this, it changes. So reorder, this gets reordered and that gets reordered, and that's how it ends up with, like, instead of 12, 8. Wow, that's pretty cool. Okay, basically puts this first, then it puts that, and then puts that last, so it reorders it. So if we wrote it like this, yeah, there we go, it reordered it essentially, even though ABC is how we wrote it. Oh wow, very cool. Okay, so this one, it doesn't reorder anything, it's pretty simplistic. So for FFI and things like that, we would want to use this. So if you have application binary, if you have a binary that, you know, or some library or whatever written in C, and you need to interpret some data that C code has put in memory somewhere, and there's a pointer to it, or you have a handle on it, then, you know, you would do this. Not that the represented in C is missing from here. Okay, so now that that's done, that was very cool. So if we look at another test, this one is going to be, actually let's call this, it's just test 1C really. And then here we can do something like this. So let's see. Actually, I need to update this this example so that this this explanation from is in there, because this is a really good explanation actually why it's 8 and not 7. But anyway, I will add that later, but let me wrap up this example with this. So let's say we just want to print the alignment and the size of as many primitive types as we can think of. So let me make a function. Let's call it pretty print and t. So let's say let's do this. T is gonna be debug, and so that means this function will take a type t. Actually, it doesn't take any argument at all, because we're gonna. So this is just we're gonna grab the. So we're gonna do this. Let's say type name. So this is like, okay, given the generic type t, what is the actual type name? What is the size of it? What is the alignment of it? And then we can do, let's say, size of, no, we need that, we should probably do something like this. No, not size of, we can say type name, and then we can say the size and the alignment. There we go. Cool. So here it'll say, okay, what is the type and what is its size and alignment? Actually, why don't we do this? Put some. Okay. Trying to make it look pretty. All right. So so here now, this should be pretty easy. So in order to run this, we would just say something like pretty print for U8, and let's see if it works before. Okay, so it goes U8, size is 1, align is 1. So let's clean this up a little bit. And then we can say U8 like this. There you go. For U8, the size is 1, the alignment is 1. Then we can say, let's just do this. Okay, so U8 size is 1, line is 1. Then we can say pretty print. Oh yeah, exactly. Let's do this. Perfect. So here we go. U8 is size 1, align 1. U16 size 2, align 2. U32 4, and nothing really that interesting here. Boolean is size 1, align 1. We kind of talked about this at the beginning. So Boolean actually takes up a byte, not a bit. So with that, that pretty much covers the alignment section. I'm going to update this, and then we can talk about global allocators next. So our next example is actually going to be pretty short. It's we're just going to be I'll just show how to use jemalloc, which is a global allocator. So the Rust standard library comes out of the box with it used to come out of the box with jemallocator, but in more recent versions that got removed, and then now it's just using I think whatever the glibc, basically libc provides. The default one, and you can actually read these articles. There's a ton of detail about like which one to use and why. But rule of thumb, like roughly speaking, if you have like for example, the Rebel TUI uses Tokyo. The Rebel TUI crate uses Tokyo. The applications Rebel Commander, they use they're all multi-threaded. They allocate lots of small objects, structs, and then deallocate them. So I haven't done extensive testing, but supposedly with that type of use case, jemalloc is finely tuned for that. So multi-threaded workloads where you have to basically create and delete or just drop lots of small structs, which is pretty much the Rebel TUI workflow. So, but yeah, feel free to read these articles in detail. There's a ton of really good information about like, why you should use this, and my normal advice, test or make sure to do instrumentation and testing. Let's see, we have allocator example. So this one, this is actually very short. So basically, just add these crates as dependencies, and let's see, once that's done, it's as simple as, let's say you make a main function, or let's say we make a test, jemalloc, something like that, and here we can say that's literally it. And then we can just say lizard green is jemalloc. That's pretty much the extent of it. And you would typically put this in a in your main, whatever your main function is. So whatever application you're writing. So if we run it, applications do the same thing with this allocator, global allocator. The other one is just that the runtime performance might be different, and then you should test to see if that this suits your need or not. So with that, that's the end of this example, and then there's 3 examples left, which are much more interesting than this. So let's go to the next one. The next example I'm going to create is a RingBuffer, which is a data structure which is essentially, it's like a vector or a stack, like a stack or a queue, vectec or vec, except that it doesn't grow. So like if you allocate it to whatever number, it's a constant number, and like if it's, if you say make a ring buffer of size 10, then if you add 11 items to it, it'll just overwrite the first item. So, and if you write like 20 items, the first 10 will be overwritten. So essentially, it's a fixed length, well, not fixed length, it's a fixed capacity data structure, and it's used for situations where, like for example, in the Rebel 2e crates, I collect a lot of performance data to figure out how long things are taking to render, and then I collect a lot of data points to create, to figure out what the sort of the average response time is, the quickest response time, the slowest response time, and then create a heads-up display, which is used in the applications. And so this RingBuffer comes in handy there, because I only want to sample so many data points, and it's expensive to sample these data points and also to perform calculations. So what I do is I have a RingBuffer, and I have some instrumentation code essentially populate the RingBuffer, and then at specific intervals, some other task, Tokyo tasks, will essentially, it's kind of like, there's like a rate limiter where only so many of these calculations can be done, in some amount of time. And so what happens is that whenever the rate limit has not been hit, the data, whatever is available in this RingBuffer, it gets some expensive computation gets done, and a result is produced. So, and the result that's produced is essentially the output of the heads-up display, which is also actually statically allocated, because it doesn't really grow. So it's not really even, it's not a vec. That also is an array. So arrays can be used in a lot of places to speed things up. So let's look at the example. This will actually make more sense when looking at actual code. So first thing we're going to do is, let's make a module. This is going to be RingBuffer, and this RingBuffer, it's redundant, but I mean, this one is not going to be heap allocated. This one's going to be stack allocated. We can actually absolutely have a heap allocated RingBuffer as well. So what I want to do is, before we get too far into it, I wanted to let's say look at the API first to see what this like RingBuffer should do. So like for example, so this, since we know that it's going to be a RingBuffer, and the RingBuffer is going to be generic over type T, but also generic over const n. And this is actually this is what this means is that there's going to be an array basically, which some number is going to be passed. So you'll see this in smallvec and smallstr as well. This is how this works. But so what you're saying is that make a RingBuffer given this generic, this type. I'm going to substitute this generic for real type, and then this const usize type, which I can't provide the type. It's not generic in that sense, but I do have to provide a number before I can use the RingBuffer. So we're going to have an internal storage of not T and N. This is not going to work for us because like since the RingBuffer itself is allocated up front, we don't know what's actually, whether it's none or some values. So we're going to make it optional of type T. But for the purposes of sizing this RingBuffer, it's going to be the size of T multiplied by N. That's roughly what this internal storage size is going to be. So in addition to that, I also need a few other pointers, but we'll get to that later. So let's do this. Let's write out what this API is going to look like. So it's a RingBuffer inline, and this module is going to use, okay, just a bunch of tests. And let's see what the let's look at what the so remember I said you can implement a queue API or a stack API. Let's just do queue for simplicity. In the Rebel 2e code base, you'll find like a proper implementation of RingBuffer, which is stack allocated and heap allocated. So if you want, you can look at that code in the Rebel open core repo. And there's links to that in here. So if you look at this article, it has all the stuff that I'm saying in there. So so let's see. Okay, so let's see what the queue would look like. So the first thing we need to do is let's make a RingBuffer. This is like kind of like almost like test-driven development, but not really. So here we're going to say something like that, where obviously the new constructor doesn't exist, but we're going to say something like, make me a RingBuffer. The concrete type that you'll replace T with, the generic T, is going to be U8, and then the actual N, which is a const of usize, it's going to be 4. So I'm substituting these parameters with these arguments. So then let's say we want to do, like, say, partial fill use case. So here, what that looks like is that we can say RingBuffer, we can say push 1, let's say push 1, 2, 3, and then we want a couple of things. We want to say assert, the length and the capacity. So we want to assert that the length is 3 and the capacity is 4. Why 4? Because that thing. And then, so obviously we don't have any of these methods yet, but we're gonna make it in just a second. So then, so this is a queue API. So when I remove something, because it's an array, it's gonna shift all the items to the left. Typically that's what would happen. But because the RingBuffer, the beauty of the algorithm, this is where we're going to have a head, tail, and account, head, tail pointers and account usize in the struct. What'll happen is that when we remove, it actually won't do anything. It'll just advance one number. And so the contents of the RingBuffer don't get affected. So it's an extremely fast, extremely efficient from a memory locality, latency, allocation, deallocation performance perspective. This thing is really, really good. So so let's see if we say a equals, we say remove. So remove's basically gonna pushes. It's like a queue. So when you push, it'll which is the head, which is the tail. let's see. Q. If I insert 3 items, which is the head and which is the tail. Forget. I see. So the head points to the oldest item and the tail points to the, got it. So 1, 2, 3, the head is 1 and the tail is 3. Makes sense. Okay. So when I remove from the, like in this case, I'm going to remove 3 and, no, is it removing? Actually, this is you know what? I'm just going to do this. I'm going to say add and remove. So when I add, the semantics of my add are going to be, I'm going to, let's say, add the head of Q. And when I remove, I'm going to remove from, let's see, if I say, actually, this is not really a queue, this is a stack. Yeah, I think this is a stack, so, oops. Okay, so we're just gonna basically push and pop. I guess I'm calling it add and remove, but yeah, so add adds to the head. So basically, if I add if I add 1, 2, and 3, when I hit remove, I expect to remove 1 first, so it's a stack. Okay, so never mind. I meant to say stack, not queue. Okay, so we add to the head and remove from the head. So that's why it's a stack. So if we do like this and then we do like that, so we can, when we make the assertion, A should be, since we added 1 first, when we remove it, it should be 1. It should be 2, and it should be, and later on we can rename this push and pop. That I don't know why this is called add and remove, but it should just be push and pop to remove to disambiguate its use from a queue. Okay, so let's see. I think I need to make this bug fix in the sample code that I have. Pretty sure this is stack. Yes. Okay, so then another kind of behavior that we want, and notice I haven't implemented it, but there's kind of like to-dos happening. So for the implementation block, the syntax looks kind of like that, and I'm gonna let the Copilot fill all this out in a minute once I give it enough of the API. That's kind of like what I'm doing. So this is a to-do, and there's more to-dos here. We're going to do head, tail, and count, and here we're going to do whatever, add missing methods. Okay, that makes sense. And all right. So now the tests that I am writing are going to cover a bunch of different use cases for this API. So one is partial fill. So I haven't actually used up the full capacity. Then the next one is I'm going to fill it to the capacity. This is fill to capacity use case. And finally, it's going to be overfill. Overfill the RingBuffer. That means we're going to fill it beyond the capacity. So the capacity, I'm going to add and remove items, add to the head, remove from the head, and these are going to be like that basically. So yeah, I did the right thing. So overfill is going to be something along, so I'm going to add like, it's going to be like this, but actually it's going to be more like this. So I'm going to do, actually most of this is good. So I'm going to do 1, 2, 3, and 5. So when I add 5, it's gonna basically overwrite 1. So it'll wrap around. So now when I make the assertions, it should be 2, 3. 5 and because 1 is gone because we've clobbered it with this. This is overwrites the oldest element. So this, in a nutshell, is the API. So having created this API, let us see what Copilot can do to help us actually implement it. So that's right. Let's see if it can find the. Okay, so this one, this is almost right, sort of. So if I actually constrain the type T to copy, this will work, but I don't want to do that. So instead, there's a little trick. Not much of a trick, but what I can do is instead of this the syntax where, you know, because I'm not willing to type constrain this to copy, I could, but I want to make this as flexible as possible. I don't want it to be so that you can just put copy. So here I can say, okay, put unit, which is you know, basically unit type, into this thing, and then map over it and just replace the unit items with none. So this basically gives me a constructor for internal storage, which gives me an array allocate, you know, of n items, each of which contains none, where the size of each of these items is the size of t. There you go. So that's the new. But then there's all these other functions like add, length, capacity. So let's see, we got pub fn length, then pub fn capacity. So capacity and length, that's pretty straightforward. So we obviously haven't computed, you know, how count is calculated, but this is pretty easy. Cap, that makes sense. So now all we have to do is implement add and remove. So, and by we, I mean, I'm going to ask Copilot to do it like that and to remove. So there you go. No big secret here. It's a modulus operator, the super awesome modulus operator, which essentially wraps around for, yeah. So, okay. So let's run this and see if our test pass. Well, what do you know? The test passed. And that was basically it. I mean, Copilot did the bulk of this implementation, but that is us creating a queue. So if, so I'm sorry, stack, keep saying queue. I really want this to be a queue. So let me verify this, and I'm going to say base r add and remove stack operations. Should they simply be renamed to push and pop, which is what I'm leaning towards. And let's see what this says. It's probably going to say yes. Other queue operations. Wait, what? Did I screw this up? Add inserts to the tail. 1, 2, and then 3. Oh no. So guess what? It was actually Q. I mess this up all the time. All right, let's see. Okay. All right, so it is actually NQ and DQ. All right, so this is, we are not adding, oh man, that's right. So it's 1, and then 2, and then 3. And then when it's removing it, it's removing 1, 2, and 3. Oh. Both inputs at the same end, operations the opposite end. Oopsie. So NQ, DQ. Maybe I should just use NQ, DQ instead of add and remove. Let's see. Nope, this is to the tail of the queue and remove from the head of the queue. Okay, and in the Rebel 2 code base, there's more sophisticated implementation of RingBuffer where I also implement an iterator, so it's much easier to kind of see what's happening there. But let's do this. Let's call it NQ, and we shall call this DQ. And I'll update the examples with this actually. That makes sense. This is NQ and DQ. There we go. All right. So when we NQ, we are NQing to the tail, and when we're DQ, we are removing from the head. I makes sense. And if we actually look at the RingBuffer implementation, yeah, that's what it's doing. So yeah, it takes the head, moves the head forwards. So basically, the 0th element is the first item, moves the head, so 1, 2, 3, and then when it removes it, it goes 1, 2, 3. Okay, makes sense. And that's why we have a head and a tail. Okay, makes sense. Perfect. Okay, that confusion is cleared up. So that was the Q API. So I mean, this wasn't really supposed to be a video about how to make a RingBuffer, the algorithm for RingBuffer, but it was more like, this is a data structure that has a size. So let's, if we size it, what will that look like? So if we do like this, we can say size, and let's say we can do, actually, we don't really care about alignment. Compiler takes care of it. So we can do something like size of RingBuffer is 32. So it's essentially U8 is 1 byte times 4. Oh, right, but why is it 32? Let's see. Is that right? U8 4 times 32. Let's see. In bytes, so T of n would be, but if it's 1 byte, U8 is 1 byte, and that's 4, why is it saying the size is 32? That's odd. Of course, it's 32. So the internal storage, oopsie, my bad. So if we had done size of the RingBuffer's internal storage, so this is the whole RingBuffer, but the size of the, let's say, size of internal storage. This is what I got myself confused. So the size of the internal storage is 8 bytes, but the size of the entire RingBuffer is 32 bytes, and that's correct, because that is correct, and that is because if we look at the RingBuffer, that thing is, let's say, where's this assertions? So we can say size of internal storage is going to be 4, because it's 4 times U8. U8 is 1 byte, and the size should, there we go, 4 for head, 4 for tail, 4 for count, and 4 for internal storage. I forgot the 4 for internal storage. There we go. Okay. That should work. No, 4. Oh, wait, what? What is it doing? 1, 2, 3, 8. Oh, wait, what? Size of internal storage is 8 bytes. Interesting. Not 4. Why? Oh, is it because of option? Of course it is. This is my bad. So the reason it is not 4 bytes is because 4 bytes is, so each item is 1 byte. So option U8, which is actually, how many bytes is the option of U8? So let's find the size of it. So let's see, size of option of U8 is that, what is that? 2. Okay, makes sense. make sense. It isn't 1. So the size of U8, so if we say let size of U8 is that, so let's look at this. So I know we can actually just abort the program here. So the test won't run, but we won't see all the other outputs. So it says size of U8 is 1 byte, but the size of option of U8 is 2 bytes because you don't get something for nothing. So the U8 is 1 byte, but whether the existence of U8 or not, let's say you can think of it as a Boolean, it's 1 more bit that you need, but that 1 more bit, because of the alignment reasons, that 1 bit ends up taking a byte, and thus it's 2 bytes per slot. Man, these videos are awesome. It helps me really kind of like dig deep into these things. Okay, so size. Oh, so now we know that this is RingBuffer. Actually, let's do this. I don't like writing this over and over again, so let's just do this. Let's say, so we're going to say type my RingBuffer is that, and I'm just going to replace it. That way there's no typos, and I'm not having to type these things over and over again. Why is this not? This should just be my RingBuffer, and this should also be my RingBuffer. That was odd. Okay, so now we have size. Okay, so size of U8 is, we can assert that to be 1, and we know that the size of optional U8 is 2. Now we can calculate the size of my RingBuffer. So my RingBuffer would be the size of the internal storage. So the size of the internal storage is going to be 4 times 2, which is 8. 8, and each item is 2 bytes, and there are 4 items. And then this one is going to be, actually, let's see, is this correct? Internal storage already, this is wrong, because internal storage is 8. And so, let's see. I'm not sure where it's getting 444. Let's go look at RingBuffer real quick. So we have, oh, I see, usize, usize, usize. That's, why is that 4? That should be size of usize, which is a 64-bit system, so 64-bit bytes. 64 divided by 8, which is 8, so it is not 4. Ugh, what is this? So it's 8 usizes, right? So we got 8 usizes. This is 3 usizes, and this one is the whatever internal storage. And that should do it. Then remove this weird comment. So this should be, ta-da! So there you go. Okay, so that goes into the nitty-gritty sizing, and all of this is, in this case, heap allocated. I'm sorry, this is stack allocated because I'm allocating inline. If I wanted to heap allocated, I would have to change the internal storage to not an array, but a vec of this option of t, basically. Actually, let me see how I did it in the Rebel 2e codebase. Why even use a made-up example when I have a real example? So let's look at RingBuffer. Let's see. I think I have like heap. Let me do this. Code insiders, new Rebel open core. Let's go look at this and see what we have here. Buffer. Okay, here we go. So we have RingBuffer. This is the real RingBuffer, not the made-up one for this this example. This is the Rebel open core, the Rebel 2e crate in the Rebel open core repo. So we got, okay, so the stack is exactly the same. Oh, excellent. That's the same exact implementation, or close enough. RingBuffer heap. So for RingBuffer heap, we got, vec. Perfect. Another option, instead of using vec, we could have also said box. You could just box this. So you could say box, something like that. You could do that. So it doesn't have to be a vec. It could be a box of that. So whatever. I ended up using vec because I use with capacity. Remember that with capacity method? You can say vec with capacity, and then n is a constant. So, and you know it's never going to grow. So this internal storage is never getting reallocated, because this algorithm will guarantee that it won't. So, okay, excellent. So with this, I think that was the example for RingBuffer and the queues, and a little bit of confusion about the adding to the header, the tail. So with that, I think there's only one example left, which is how to use small. Wait, actually, let me see how many examples are left. Is it smallvec? Oh yeah, looks like it's just smallvec and smallstr that's left. So yeah, the next example is going to be that. So in the next example, we are going to use the smallvec and smallstr crates, and they're replacements, not replacements. You can think of it as inline equivalents for string and vec. So smallvec is the equivalent for vec, and smallstr is the equivalent for string. Only difference is these are inline, meaning like they're stack allocated rather than heap allocated. There's some caveats to using them. Like you can't use it quite. I mean, you could for the most cases, but I'll point out where there's things to watch out for. And I'll do them as I'm making these examples back. So let's look at inline. I call it inline because smallstr sounds whatever, but let's do this. We need cargo, add smallstr, and I'm also going to add smallvec. Why not? So that should be in our cargo tunnel. Excellent. And then, so here, what were we going to do? Okay, so we okay, so we added that to lib. Perfect. So here we're going to make a configuration InlineVec example tests. Okay. So let's see, smallvec. So let's see, should we start with InlineVec or smallvec? Let's start with smallvec. So actually, InlineVec is something that I made to make it easier to work with smallvec, and so we're like smallvec, InlineVec, and I have macros also to make it very easy. It's kind of like vec replacement, and then same with smallstr and InlineStr. So for now, I'll show you smallvec first, and then I can show you InlineVec. So smallvec is this thing. So we say, let me make a smallvec. So in order to use smallvec, is very similar to what you saw with the RingBuffer. You have to say something like this, my smallvec. You have to say smallvec, and then you have to say like smallvec of what. So same thing. We did this, the t and the n, same. So t and n. And then now we can say, let's say we make a test, and here we say new smallvec. So let's say we can do there's two ways of doing this. We can do with new, and we can do with macro. So if we do it with new, it's actually very similar to what we saw with the RingBuffer. So that's because this under the hood does something very similar to the RingBuffer, except that this can spill into the heap. That's its thing, that it's special. So here we can say my smallvec new, and then so how many are it's capacity of 4. So I'm just gonna put let's say for I in 0 up to 2. So I'm gonna put, so this is gonna be 0, 1, 2. Yeah, okay. So I've put, like, 0, 1, and 2 in there. This is that range operator. It's including 2, up to and including. So as opposed to just before 2, this is including 2. So here we can say assert the length is 2, capacity is 4. So capacity is 4. It doesn't matter. Like, we can assert the capacity here as 4. The length over here will be 0 because we haven't added anything here. But here the capacity won't change. The capacity is always going to be 4 because it's not growing. And here we can say if I so there's 2 ways of accessing this. We can actually use the array accessor syntax, or we can do similarly, we can say acc.get 0. But then this will be sum and a reference to a value. So that's the big difference in the syntax between these two. So if we run this, yeah, that works. So here, if I then say like that, that works as well. So not that interesting. So this is just like, like a what you're used to seeing with Vec, but you can spill it. So if I add even though this small vec we've said is U8, 4 U8s. If you add a 5th U8, it'll spill. And so I can demonstrate that here. Actually, let's show spilling. That's new. Let's do this. Fn test spill. So to spill it, we can. What's it doing? Let's see. Let's remove all of these. So we're gonna add whatever. So it's supposed to have like 4 items in it, but now I am adding clearly more than 4. So here we're gonna see, okay, has this spilled? So we're gonna say assert equal accumulator. It has not. How can it be spilled? The capacity is, the length is 0. But here it should be spilled because I've clearly put more things in it. So it's spilled out of the, this is still in stack, spilled to heap, which is really cool. And of course there's a cost for when it spills from the stack to the heap, because they have to be copied into the heap, and mem copies are slow depending on how much. I mean, if you have a lot of data, then yeah, mem copy is going to be slow. So there you go, that's spilling. But I wanted to show, in addition to the new method, there's also a macro, and the macro looks something like this. You say let mute acc, you say smallvec, and whatever, actually 0, 1, 2, something like that. And then it's complaining because this is a macro. So when we use the macro syntax, we have to, for Rust compiler reasons, we have to do this and spell it right. There you go. What the heck? So now the compiler's happy because it's like, oh, okay, cool, I know what you're doing. So so here we can do, same thing, capacity, whatever. Yeah, 0, same, nothing. And actually, yeah, that should be none. Let's see if this works. There you go. It's not out of bounds. Let's see. Oh, it's actually with get. Let's see. This is out of bounds, but you won't see an error. But if I say 4, this will blow up. Actually. Oh, right, because it's expecting a number, whatever. Doesn't matter. It's gonna blow up anyway, so it doesn't matter what I put here, whatever. Irrelevant. Okay, so this doesn't compile. Excellent. So that's the how to use smallvec using new, using the macro, and it also has a width capacity, so you can. It's kind of pointless because, well, since when you create it, you have to statically allocate it. Here, the width capacity, I guess, I don't know. Maybe there's some logic there in some use cases. Width capacity might make sense, but probably, well, I guess you could do something like this. You can let's say in this example we've allocated a smallvec to hold 4 U8s, but if I say width capacity, because I can say width capacity, there's width capacity. So if I say something like let mute actually something nonsensical like 40, right? Like clearly, or even 10, like whatever is more than 4. Like I know that it's spilled because it was supposed to have, like, obviously it's spilled. The backing store only has space for 4 U8s, and I'm asking for 10 U8s. So if I say assert EQ, spill. What's wrong with this? Oh, spilled. And so it should be true. Let's verify that hypothesis, and that is correct. It makes sense, right? I mean, I told it that okay, you should statically allocate 4 items. Then I'm saying, oh, now allocate 10 items. So clearly it's not going to fit in the stack, so it puts it on the heap. So there you go. It's a way to use essentially vecs that are inline vecs, and for the just to make this easier to use, if you don't want to kind of use it that way, I have an equivalent called InlineVec. So here we can say fn test InlineVec, and it's essentially the same thing. Essentially, what's wrong with this? So here, the reason this is easier is because you don't have to specify the static size. I'm making assumptions about how many. So this is those caveats. If you have a lot of items that you're statically allocating, or if the size of each item is very big, then there could be situations where you run out of stack. So you get stack overflow. So you got to be careful with that. So like, for example, if you look at InlineVec, it says, okay, it's a small vec of t, InlineVec size is only 8. If I made this like a much larger number, then you can have some significant problems. And also, you have to be careful because if you make some of these numbers really big, it'll end up slowing down your program. So it's not like you have to be really careful. There's all kinds of tuning that you have to do. See, if you make this certain numbers too large, then it messes things up. It doesn't necessarily do what you think. So be sure to test your assumptions and your hypotheses by instrumenting afterwards. So okay, so the reason this is easier is because you don't have to make a my small vec, and you don't have to say the size. And just kind of cleaner. You say, oh, make me an inline vec. Cool, awesome. And there's also with capacity and all that kind of stuff. And the rest of it just works, you know, the same. So there's not a whole, oh, oops, what the heck? Let me just delete this. Okay. What is this? Oh, why is it 4? The capacity is clearly InlineVec, which is 8. So this is wrong. And let's see. Oh, right. This is still 8. Okay. And the rest of it works the same. So it's meant to be a drop-in replacement. So if you've watched my, there's a video I did on new type pattern. If you watch that video, and let's say you're like, well, shouldn't we have like InlineVec new type pattern? So shouldn't we have like, instead of U sizes for everything, what if we had like a notion of length? So what if we had like length of type length is then of, let's say 5. So it just so happens there's a length struct and a length function. So now we can have a length. And so this is like the, if you think about the capacity, like, oh, actually, why is it 5? Let's make it 8 like the others. Wait, is this 8 or 5? 1, 2, 3. Okay, let's just leave it 5. It doesn't really matter. Okay, so so let's say that I want to make something like this 0, 1, 2, 3, 4. Yeah. So like I want to make an inline vec hold, you know, these values. So how would I go about it? So I could say, okay, well, the length is 5, and then what's the max index that I could have? So we have an index type, which we can import, and then we can say something like take the length and convert it to an index. And this is that the new type pattern. So it's like a very type safe way of doing this. It does a -1, so max index is 4, and the length is 5. But you know, okay. And then so now we can do something like let us let's say for range inclusive. So 0 including max index. Notice I didn't say length, I said max index. So let's see, actually there's an easier way to do this. You say as U size, and so this you can also put like these, but whatever. Why is this not working? Oh, right, because that's not U size, that's something else. Okay, never mind. Let's just do as U size. Okay, and so now we're saying, you know, from 0 to max index, we want to put something in this. Let's make a, let mute ec. Let's make one of these, and this is going to be an InlineVec, and why is this being strange? That should just work. What is this? Type annotations needed. No, not really. Then we say push. Yeah, okay. Okay, it was just a compiler type inference thing. So here we can just push. I don't know why it's saying as you wait. There we go. So now we're pushing 0, 1, 2, 3, 4, and then now we can, you know, we can do something like. So we can say assert, let's see, let's run this test. And then so we can say something like assert capacity is 8. That's right. And then we can do some spot checks. So we can say, okay, now that we have put 0, 1, 2, 3, 4, let us see what is at accumulator. I guess we could do like this, max index as uses. So max index should be basically the value is the same as the index. So this should work. There you go. So I mean, I could have just said this as well. I mean, but whatever. That test is hard to read. This is easier to read. Something like that. So this shows how to use InlineVec with all these interesting types like length and index if you don't want to use the smallvec directly. But yeah. So this is the second to last example. And the final example is just going to be using smallstr, which uses a slightly different pattern, which we will get into next. So in the final example, we're going to be looking at smallstr. And it's just like, it's the equivalent of smallvec. It's built to be using smallvec under the hood. It's just that I am, in the Rebel 2 crates, I have a nicety built on top of something called InlineString with a macro, which makes it really easy to work with. But let's do the same thing as we did in the example 5. I'll show you the let's see, InlineStr example. InString. Okay, and let's go look at this. There we go. Where's this? Okay. So here, let's start the same way as we did before. Yeah, let's make a module just for tests inline. Actually, this is going to be inline. No, this is smallstr tests. We're going to do smallstr tests, and we're going to do InlineString tests. Okay, so let's do the smallstr first. I think we already added this to our cargo toml. Pretty sure. Oops. Yes. Okay. So that's been added. So let's do this. So we're just gonna say kind of like simple use of smallstr. Like it's not really that. There isn't a whole lot to show, but I will show. Like yeah. Let's see tests new. It's very similar to what you've seen already with the other pattern, with making an array. So you say small string, and the same kind of thing. Like you have to say like how big it is. So you have to say like actually delete all this. So you have to say, okay, make me a small string. Actually, maybe I should just make this a type like in the other examples. So we can say type my small string, my small str, and here we can put, instead of all that, my small str. There you go, much cleaner. So we're saying, okay, make me a small string, which the backing store is 4 U8s. And the same thing, it'll spill because it's using smallvec under the hood. It's just that this is optimized for use with things like debug display, any struct that implements debug or display trait, where you would normally use a format macro or the write macro using a formatter, or just anything that can implement the write trait. You can use this. So I'll give example of this right now. So there's a couple ways to write into this. So let's say I wanted to add like some items to it. So actually let's do this real quick. So I'm going to assert that the capacity is 4, length is 0, empty is true, yes, and it is not spilled. So that should hold true, and it does, not a surprise. So now I'm going to write something into the inline string, or smallstr, whatever. So here you can say, like, you could do like this. You can do let's see, can we clear? Yes, we can. Okay, so we can do like this. We can either push stir, just like string, and then now we can say assert equals accumulator is ABC. That should hold true. So this smallstr, it implements deref. So that's how this works. And so check that out. It works. You can also just put this here. That's as ref. Same thing. It's yeah, you can look at the implementation of this. That's some really cool cool things they've done to make it ergonomic and swappable with string. For the most part, wherever you can use like string, because this is owned. In order to get it to a string slice, you just have to put an ampersand before typically. So you can do like this. And so, like, for example, you can say it equals, and it'll show you like, oh look, it's no, it's a reference. Never mind, that wasn't very helpful. So you don't need this. You can just do like that. It's smart enough to deref. So instead of doing this, we can also write something using the write macro. That's another way. This is using push stir. So let's clear it out. So you can say act.clear. So even when I cleared out, like, it's still allocated in the heap. It just basically it's null terminated. So just it just adjusted itself internally. So there's no performance implication to do this. This is safe to do. I mean, fast to do, not safe. This is all safe. So here we can say, so it kind of goes like this. You say write macro. Before you can use the write macro, this is really, really annoying. You have to say use stud format write. Because if you don't do this, this will complain. So now you can do, I said unwrap because you can typically, I mean, it's up to you. You can do like this. You can do like that, whatever works. So here, because I think this will, does it return something? Let's see if it returns anything. Nope, it doesn't return anything. So yeah, you can do like this. And why is this putting so much stuff? Oh, I see. Okay, whatever. So it's going to be hello world. So there you go. And this is spilled for sure. Let's see. Assert. Because 13 is greater than 4. So ec spilled true. And then there you go. So that's how you use smallstr. An alternative to that is you can use this is what I wanted to show, InlineString. It's very similar. It's just a little bit, syntax is less, it's easier, I think. So we can say test new, and we can say fn test macro. We'll do both of these. So with test new, we can say something like just InlineString and like that. And so we have like a new inline string, and then it's almost identical actually to what we did here. We can write to it just like we would write to this. So just to show slightly different syntax, we can do like this. And then note, if you don't have this import state or this use statement, you'll see this light up red. And now we can assert equals that this is indeed hello world, and this will have spilled just like the others. I'm not gonna just get some, yeah, there you go. So this is spilled just like the other one spilled, because if you look at it under the hood, it's just a small string. So you can say assert spilled is true, Split is not true? Why not? Ah, it is not true because this is much larger, 16 bytes, that's why. So let's look at the capacity. Okay. So nope, its capacities, it even says right here 16. So assert EQ, and this will be false because this is only 13. Yeah, okay, there you go, cool. Oh, that was nice. And then the macro, this let me give you a real example for this would come into play. So let's say we have like a struct that we make called demo, and there we have like an ID which is an U8, and we have a name which itself is an inline string. So let's say that this is our, you know, clean. We can size this, allocate it fully on the stack. Does not need to go to the heap. So here now we can say implement standard format display for demo. And here I can say something like whatever. You see that write macro? See the, because you know this is name, which is an inline string, and write macro works, so that's why this works. That's nice. And then we can do something like this. We can say, let's see, let's make a demo instance. Just call it demo1, and it'll be whatever. So instead of inline string new, check this out. We have a macro, and this macro basically uses format arg. So you can use this as a drop-in replacement for format, or for print line, or for yeah. So it essentially does the same thing, and it's got a nice the macro implement. I did a video on declarative macros, so this is a nice one. Okay, so let's see. Okay, so I think now what we can do is that we can say let demo1, it's not really to string, we can say to inline string, right? We can say, so we can say, you remember it was a drop-in replacement, so we can say inline string. So the difference between this and format is that format will generate a string and allocate that on the heap. If you use inline string, it doesn't make a heap allocation, it just stays on the stack. So if you know your string is never going to change, it's like essentially an immutable string and it's small enough, then this might make sense. But if it's a, you know, multi-megabyte thing, probably not a good idea, because, you know, your stack is typically, like on Linux, 8 megabytes for the whole process. So now that that's done, we can say assert. So basically we could just use it just like we would string or whatever. It's very compatible. Like there's nothing strange about it. So it just works. It's like drop-in replacements for this and drop-in replacements for that. And let's see, is that all I wanted to show? Yeah. So this is kind of like if you want to make a display implementation and you don't want any heap allocation, or you don't want, like, you know that your use cases are tiny enough, then this is actually pretty efficient if you think about it, because no heap allocate. It's all like localized to the stack, right? Because notice this is inline string. This is no allocation if you on the heap anyway. Actually, it's no like allocation anywhere because this has already been allocated. This writes into the formatter, and the formatter is supplied by inline string, which itself it's a new inline string. So you could actually just make a new inline string. So you can do something like this instead of this macro. You can do another variant of this actually. Let's do this. So demo. Let's call this demo1. Let's do demo2. So here, let's say foobar and what the heck, demo2. So here instead of saying inline string, what we could say is let mute inline string. So we're making a new inline string of some size, and then we have to use that standard format, right? And then I can just say like, okay, write into this given buffer this thing, hello demo2 name, or actually this is completely redundant. We can just do this because this has a display trait implementation. And then now we can look inside of the ACK and we will find this foobar. So that's another interesting way of using it if you want to, like if you think about it, this demo2 struct is allocated on the heap. This is allocated, sorry. Demo2 struct is allocated on the stack. This is allocated on the stack. This ACK thing is also allocated on the stack. This is basically, you can think of it as like format output holder. So this basically holds some place in memory, like where you're gonna take the display trait for demo2 and render it into this output format, right? So so format output. Actually, why don't we just call it format output? Yeah. So then this does that, and then we can look inside of this format output thing. So here we have allocated. This is allocate space on heap. So but not. I keep saying heap. My goodness, I really want to allocate something on the heap. So we are going to allocate this on the stack, and then FMT output basically is on stack. And then here we didn't say format, which would generate a string. There's no need for that. So we can just say, okay, just write into this format output struct whatever you get from the display trait implementation of demo2, which you can see here. So yeah, no heap allocations. We've scoped it entirely to the stack. If that is something that matters for your use cases, this is one way to do it. So this has been a video, I think, months in the making. I think I've worked on this for about a week now. So with that, we have come to the end of this video. If you like this video, please thumbs it up and subscribe to the channel for more. Please check out this article in Developer Life. I'll also link this issue and this article to the video description on YouTube. And then if you want to leave comments and feedback, please do so in the issue. Or you can reach out to me on LinkedIn or over email. And if you have any feedback on comments on this, because I turn off comments on YouTube and I have abandoned Discord. So this one, I would rate, if you like this, if you've stuck with it this far, these are some really good examples of real world code examples of using this in the Rebel TUI crate. A lot of stuff in there that might be worth taking a look at. A lot of situations where you don't want to go to the heap, you want to stay on the stack for whatever reason. There's ways to do it. Or you don't want to allocate a string to, let's say, format a struct into its display output format, or what do we call this here? Format output. You don't want to allocate a string for that. Then there's facilities provided in Rebel TUI crate to allow you to not do that. Whew. So with that, thank you so much for watching, and I hope you enjoyed this video, and I will see you in the next one. Take care.